Hello, my name is Ryan McBee. I am a research engineer from Southwest Research Institute, and today I will be talking about the use of low-precision mathematics for real-time machine learning on resource-constrained FPGAs. A bit of the motivation about this research before I get into it. Machine learning, and particularly deep neural networks, have really shown their usefulness in greater levels of autonomy, particularly for tasks where non-machine learning techniques have really proven unsatisfactory. And one of the things that we want to do for deploying these on very resource-constrained space applications is to try and design a deep neural network that is extremely efficient to allow for low size, weight, power, and cost for essential space applications. And just to make clear our objective, we want to develop a methodology for the deployment of high performance, high accuracy deep neural network inference to computationally constrained FPGAs using low precision mathematics, which I will describe later in this presentation what that more exactly means. So what is the current efficient deep neural networks? For this research, we're mainly focusing on convolutional neural networks, which are neural networks that use convolutional layers to extract information from typically image type data. They use convolutional kernels from traditional computer vision plus nonlinearities and other deep neural network features to extract richer and deeper features, as shown on the right, with an extraction of edges to facial features to full faces. Deploying deep neural networks is not exactly straightforward in some instances. A lot of the deep neural networks are trained using 32-bit floating point mathematics, which it uses a fair amount of memory compared to int8 integers, and usually requires specialized computation platforms to actually do the floating point computation. Additionally, a lot of the deep neural network research in recent times has, to get greater accuracy, have done less and less efficient neural networks in a pursuit of actually getting higher accuracy. All these different features do not make them readily available for resource-constrained systems of using deep neural networks. So what have they done to make these more efficient? Some of the key techniques that have been used have been to replace the normal convolution layers with deep depthwise separable convolutions. These break apart the dense convolutions into a depthwise convolution and then a pointwise convolution that then combines all of that data. This creates a structured sparsity that allows for roughly 9 times fewer computations with near original accuracy to the dense convolution. Additionally, the 32-bit floating point mathematics used can be converted down into 8-bit quantized mathematics. And using asymmetric quantization and fine-tuning, you can get near original accuracy to the floating point weights. So with those in mind, those seem pretty good, but we want to go even further. We want to make our algorithm even efficient enough to run on the most resource-constrained systems, particularly the ones for space applications. And so to really nail this down, we want to tackle minimizing the memory movements, which is the limiting factor for most deep neural networks. The image on the right showcases the amount of energy used for different types of operations for a particular CPU. And the two most energy inefficient operations are both memory reads to off-chip RAM and to L2 cache. And so by minimizing our memory reads, we can have the greatest reduction in power usage and make our deep neural network much more efficient and allow it to run on resource-constrained systems. So to do this, we hope to use low-precision mathematics for the deep neural networks. So what is low-precision math? Low-precision math, and by our definition, is any mathematical floating point value that is quantized to use 4 or less bits. So that is anywhere from 16 values, 8 values, 4, 2, and 1-bit values. And there are 2 different places in the deep neural network that you can actually quantize these values. You can quantize the inputs to each layer, or you can quantize the weights to each layer. And the input refers to the data that comes into each neural network layer. And the weights refer to the trained values that give the neural network its learned capability. And the most popular low precision technique is the binary neural network. This is the most extreme quantization in which each input and each weight is represented by a single bit, which can represent a -1 or a 1 +1 value. And by quantizing to this extreme case, it actually has some very interesting mathematical properties, including the fact that the multiply can now be done using an XNOR operator, and addition can be done using a bit counting or a population count. And both of these operations can be done very efficiently on resource-constrained processors, and most processors, including microcontrollers, GPUs, CPUs, FPGAs, have some form of support for accelerated computation of these types of mathematics. The next type of computation is the ternary neural network. So this takes the binary representation and adds a zero state to it. This zero state represents removing that computation from the actual calculation. And this can result in a great amount of sparsity in your system on an order of sometimes 70% plus or minus, depending on the different circumstances. And this ternary representation allows for a great reduction in computation from a greater sparsity, but it also increases the accuracy from the binary neural network by adding an additional quantization step by 50% from 2 to 3. The next type of quantization is the n-bit quantization. This is very similar to the 8-bit quantization mentioned earlier, but represents any bits kind of bit representation that is available. As you look in the image in the bottom right, this is roughly quantized to 16 bits of precision, or 16 steps of precision for a 4-bit representation. And so this is the most generic and flexible form of low precision quantization. And so to train the activations of these low precision quantizations, the training step for these deep neural networks have to be slightly modified. Traditional deep neural networks have to have fully differentiable activation functions to actually allow for proper training, whereas the binarization step used for a single bit does not actually have a differentiable form. To make it work, they use what's called a straight-through estimator, where on the forward pass of the neural network, they actually do the quantization, but on the back pass, they approximate the derivative using an equivalent, and some examples of these are shown below. And then another key aspect to deep neural networks in general, but particularly low precision, is the use of a higher precision skip connection. These higher precision skip connections allow for higher precision information to flow through the network while letting lower precision computation being done by the lower precision networks. And in most cases, the current commercially available forms use 8-bit precision for the skip connections, but this precision can be lowered to any arbitrary n-bit precision desired. I've mentioned all the good things about the low precision neural networks, but there are a lot of negatives that are associated with it. And in particular, the biggest drawback is the great decrease in accuracy. As you look in the image below, from left to right, we go from higher quantization levels to lower quantization levels. And as you decrease the quantization level to lower and lower bit precision, the accuracy gets significantly worse. And so keeping all of this in mind as we design our system will be imperative to actually getting a high accuracy, high speed, low precision neural network. Now I'm going to talk about how we plan on mapping some of these low precision mathematics to an FPGA. And we chose an FPGA primarily because it is very well aligned for custom low precision mathematics. There's an extensive pool of various different logic blocks, including lookup tables, DSPs, and block RAM. And in particular, the ones shown here are actually taken from the ultra-scale line of the Xilinx FPGAs. And by using these in various different combinations, we can implement the different low precision mathematics, the sparsity, and the other types of computation that we need effectively, whereas the other types of processors such as CPUs, GPUs, and microcontrollers can't really offer that kind of flexibility. So how do we map these techniques to an FPGA? One of our big takeaways is mapping binary neural networks to the lookup tables, particularly the 6-to-1 lookup tables of the Xilinx FPGAs. Traditionally, binary neural networks rely on 2-to-1 lookup tables to implement, or XNOR operator to actually implement the mathematics. But the intrinsic of a Xilinx FPGA is a 6-to-1 lookup table. And so we can actually expand those 2-to-1 inputs to now be 6-to-1 inputs. And taking this even further, we can get more computation and trainability by representing a lookup table as a neural equivalent. This idea comes from research from the Xilinx Research Lab. And what it does is it actually models each lookup table as a 6 binary input, 1 binary output, and you can actually, in the middle, represent that as any arbitrary operation you want, but in this instance, they represent it by multiplying the 6 bits of input by various different weights, summing them, applying a batch norm, and then applying the sign. And this is actually really powerful because now that we have floating point weights and different additions, we can actually train this like a normal neural network. And additionally, by representing the weights as how the lookup table is formed, we don't have to actually move in the weights when we do the computation. We just have to flash the lookup table once, and the weights are stored in the permutation of the 6-to-1 lookup table combination. But one drawback of using this approach is you have a very limited input and output to each of the neural equivalents that we have. This can be alleviated by increasing the input size and the output size of each effective lookup table. There are different techniques for doing this, but the equation below represents roughly how increasing the input size and the output size can affect the outputs. The equation represents X bits of input and Y bits of output. And so the key takeaway, and you can look at this equation yourself, the number of output bits is actually linear to the number of LUTs that are required. But to increase the input size, you actually have to exponentially increase the number of LUTs that are required to achieve a greater and greater input size. So with all of these different design considerations in mind, now I'm going to talk about some of the proposed design ideas that we're going to be doing for our simple CNN targeted for an FPGA lookup table. And I will caveat this with this research is very early on, and current implementations and mapping to the FPGA are still underway. But these design considerations are very fruitful in and of themselves for how to take the hardware and the machine learning and kind of marry them together. And so from what I talked about earlier, we're going to start with an efficient architecture. And in particular, we're starting with the depthwise separable convolution. And the input to this block is going to be a binary input, and the output is going to be in bits of precision. We are also, one of the very interesting considerations that we've done is we've actually used directly the depthwise convolution as a neural equivalent. So the very first, if we go back, part of the depthwise separable convolution going from left to right is the depthwise convolution. And so these are going to be operating on the binary input data. And each depthwise convolution is 3 by 3 by 1 in depth, which has 9 inputs of data. Well, the neural equivalent in its base form requires 6 bits of input. And so to create a very simple approach, we are actually going to take the 9 binary inputs, we're going to train the network, and we're going to prune away the 3 lowest weights. And this will give us 6 binary inputs to the depthwise convolution, allowing for direct mapping of each depthwise convolution onto a lookup table. And we can either binary or in-bit output precision, allowing for various different design considerations based on the accuracy that we desire. The next part is the pointwise convolution. Going back to this depthwise separable convolution, the pointwise is what combines all the different depthwise convolutions together to actually form the in-bit output that we desire. And unfortunately, we can't directly use a neural equivalent for this step because the typical pointwise convolution has anywhere from 32 to 192 inputs. And so to represent this now, we are actually having to use a different kind of operation. And for this, we were actually going to use the direct sparse adder subtractor ternary network that we mentioned earlier. And so this is going to have a huge amount of sparsity, which is actually going to reduce the computation and allow us to do a simple binary add or subtract to our value, our depthwise convolutions that we had for the previous stage. We also mentioned earlier the skip connection, and one of the big parts that we want to do to optimize our system is to actually have some in-bits of precision, because we tried training these networks without the skip connection, and the training became very unstable and unusable. So the skip connection is a very needed part of this step. But through initial research using just the Cypher-10 data set to experiment with, we found that you can actually reduce the skip connection down from the full floating point down to precision, down to 4 or 3 bits of precision with very minimal decreases in accuracy. So those are our design considerations for our overall network. What are our next steps for this research as we currently are undertaking it? Well, our main big step is to map initial design to the FPGA to get initial inference metrics. Our design has 2 metrics we're trying to optimize for, the accuracy and the inference speed. And right now, we are working on getting the accuracy metrics, and very soon we'll have the inference speed for our designs. We want to explore training techniques to minimize the accuracy loss from doing very extreme quantization. We think there is a lot of approaches that we can do to kind of more stabilize the activation, and because low precision neural networks is a relatively less explored area than other areas of deep neural networks, we think there are more improvements that can be made over time from research and from our own experimentation. We hope to find different ways of using the neural equivalent, particularly in the pointwise convolution, to help reduce computation and increase accuracy from the arbitrary floating point weights that can be done in the NEQ. And finally, we'd like to explore other model architectures, such as the mobile inverted bottleneck used in state-of-the-art networks such as MobileNet v2 and 3 and EfficientNet. And I would like to thank you for listening to my presentation. Feel free to contact me at my email